Hi everyone, welcome to my presentation. The work of this presentation is titled Experimental Assessment of Modulation Format for Beyond 5G Millimeter Wave and ARoF Fiber Systems. First of all, let me introduce myself. My name is Javier Per Santacruz and I am a PhD student at Eindhoven University of Technology. My research topic is focused in digital signal processing for millimeter wave and ARoF fiber systems. We can see the contents of this presentation in this slide. First, the motivation of this work is showed. Next, the role of millimeter wave analog radio fiber systems in 5G is presented. The relevance to compare modulation formats in this type of system is explained in the next two sections. Then, the experimental setup to compare the different modulation formats is showed. Finally, the results, summary and conclusion of this work are presented in the last two sections. The motivation of this work will be explained in this slide. 5G is the adaptive solution to fulfill the demanding mobile traffic data requirements. Moreover, 5G has defined three types of scenarios because applications with different types of requirements are emerging. We can see these scenarios in the pyramid of this slide. On the top of the pyramid, enhanced mobile broadband is found, where to achieve high bit rate is the main goal. At the right bottom of the pyramid, ultra-reliable low-latency communication is found, where high reliability and low latency are the main requirements. At the left bottom of the pyramid, massive matching type communication is found, and its task consists of supporting a huge number of connected devices. Different types of technologies have appeared to satisfy the 5G requirements. For instance, millimeter wave cells, massive MIMO, beamforming, software-defined networking, network function virtualization, etc., etc. One of the most suitable ways to increase the bit rates in enhanced mobile broadband scenarios consists of moving to higher frequency in the millimeter wave domain. For this reason, enhanced mobile broadband scenarios require millimeter wave cells. A suitable scheme to transport the traffic data of millimeter wave cells in 5G is shown in this slide. This scheme is based on interconnected millimeter wave cells and a central office over an analog radio fiber architecture. In this scheme, first, different signals are generated and converted to the optical domain in the central office. Each optical signal is multiplexed and is related to a millimeter wave cell or remote unit. Next, these optical signals are transmitted to its corresponding remote unit through a fiber ring. Finally, each signal achieves its corresponding remote unit through a demultiplexing process. The multiplexing and demultiplexing process can be carried out by wavelength division multiplexing or space division multiplexing. Moreover, different user case examples are presented also in the scheme. These examples are the next: millimeter wave distribution in a mobile cell, millimeter wave fronthaul along a highway, and millimeter wave fronthaul distribution in a factory. Analog radio fiber system brings attractive benefits such as low latency, long reach distance, low cost, low complexity in the millimeter wave cells, high spectral efficiency, and low power consumption. For these reasons, millimeter wave cells demand analog radio fiber transport. The selection of the modulation format is key to achieve high performance in any communication system. Modulation formats have been well studied in wireless and optical channels independently. Multi-carrier waveforms are the success modulation formats in wireless channels due to its robustness to multipath. On the other hand, single carrier waveforms are the most popular modulation formats in optical channels. However, millimeter wave analog fiber presents impairment from the optical and wireless channels. Impairments like phase noise, high free space path loss, chromatic dispersion, nonlinearities from devices such as Mach-Zehnder modulators or radiofrequency amplifiers, etc., etc. Therefore, the modulation format selection has to be re-studied and analyzed for millimeter wave analog fiber systems. In this slide, we are going to introduce the modulation formats that have been compared in this work. The first one is orthogonal frequency division multiplexing, or OFDM. OFDM is the selected modulation format by the first 5G standard. Next, single carrier frequency division multiplexing, or single carrier FDM, is the standardized modulation format in the uplink of LTE. Furthermore, new modulation formats have emerged to divide the air of FDM in 5G. Three of these new modulation formats are Universal Filter Rate Multicarrier, UFMC, Generalized Frequency Division Multiplexing, GFDM, and Multicarrierless Amplitude Phase Modulation, Multicap. Moreover, we have defined one of the most relevant key performance indicators, KPIs, to compare qualitatively these modulation formats. These KPIs are Peak Average Power Ratio, PAPR, robustness to phase noise, spectral efficiency, robustness to multipath channels, and complexity. As you can see in this table, OFDM is not the best solution in terms of PAPR and robustness to phase noise. Other modulation formats such as single carrier FDM and multicap outperform OFDM in these aspects. Therefore, it's not conclusive that OFDM is the best choice for millimeter wave analog red fiber systems. The experimental setup used to compare the modulation formats presented previously is shown in this slide. First, an external cavity laser generates an optical carrier at 1550 nanometers. Next, the first Mach-Zehnder modulator modulates the optical carrier with a sinusoid of 12.5 GHz produced by a vector signal generator. Therefore, two optical tones are produced with a frequency separation of 25 GHz. This optical spectrum can be seen in this figure. Then, the signal is boosted by a erbium-doped fiber amplifier, alpha, and modulated by a second Mach-Zehnder modulator using an arbitrary waveform generator, EuWG. The spectrum of the baseband signal transmitted by the EuWG can be observed in this figure. This baseband signal is upconverted to an intermediate frequency at 1 GHz, and its spectrum is shown in this figure. The signal of each modulation format described previously is generated in the EuWG. After the second Mach-Zehnder modulator, the modulated signal are transmitted through 10 km of standard single mode fiber to a second alpha. The input power of the photodiode is controlled by a variable optical attenuator. In the PD, the two optical tones are beaten and converted to an RF signal at 25 GHz. After the PD, the electrical signal is boosted by a medium power amplifier. The millimeter wave signal is transported by a wireless link through two horn antennas with a separation of 9 meters. At the output of the received antenna, the signal is amplified by a low noise amplifier and mixed with a local oscillator at 23 GHz. The signal with an intermediate frequency of 2 GHz is sampled by a digital phosphor oscilloscope. Finally, the receiver DSP for each modulation format is realized offline using MATLAB. This slide shows two photos of the experiment. At the left photo, devices such as mixer, variable optical attenuator, EuWG, or Mach-Zehnder modulators are illustrated. This part of the experiment is very important since the millimeter wave tone generation and the modulation of the signal are carried out there. The right photo shows the experimental wireless link. The RF transmitter is compounded by a PD, a medium power amplifier, and an horn antenna, while the RF receiver is compounded by a horn antenna and a low power amplifier. The results of the experimental setup are presented in this slide. First, the under-test modulation formats are evaluated using a QPSK modulation in this graph. The horizontal axis of this graph corresponds to the optical power at the input of the PD in dBm. The vertical axis corresponds to the bit error rate, BER. The constellations of each modulation format for the maximum optical power are also presented. The error vector magnitude is presented under this constellation. Moreover, the 7% overhead effect threshold is represented with a dotted red line. It can be observed that the VER of all the modulation formats are below of this threshold from -5 dBm of optical power. Furthermore, for high power, the best modulation formats are the next following this order: single carrier FDM, multicap OFDM, UFMC, and GFDM. The PAPR of the evaluated modulation formats follows also this order. Single carrier FDM presents the lowest PAPR level and GFDM the highest one. Therefore, for QPSK, single carrier performs better at high power due to its low PAPR level. In this second graph, the modulation formats are evaluating using a system QM modulation. Observing this graph, the VER of all the modulation formats are below the 7% overhead effect threshold at 2 dBm of optical power. In this case, it can be noticed that the multicap VER is quite lower than the rest of the modulation formats. Therefore, for system QAM, multicap performs best at high power. One of the main reasons of this fact is that the used equalizer in the multicap modulation amplifies less the noise than the equalizer used in the rest of the modulation formats. Then, the equalizer strategy is crucial in this type of system. We can summarize and conclude with the next statements. Analog radio fiber is a strong candidate to be part of the Beyond 5G architecture. The performance of different modulation formats in experimental analog fiber setup has been studied. The experimental results show VER below the 7% overhead effect threshold for all the evaluated modulation formats. Experimental results show that modulation formats such as multicap and single carrier FDM overcome the OFDM performance in this type of systems. Finally, we can conclude that the modulation format selection has to be re-evaluated for millimeter wave analog fiber systems. Thank you for your attention, and I am glad to answer any question.